Okay, welcome guys. Welcome back from break. This is Physics 390 class 19, and it's on degenerate perturbation theory. And this comes from chapter 7.2 of our textbook. We're going to see what to do when we try to use perturbation theory, and we'll stick with two in general. Two or more of our energies of our unperturbed states have the same energy, which gives us problems with the formulas which we found in non-degenerate perturbation theory. Okay, so let's check this out. So the need for degenerate perturbation theory. Well, up at the right here is our expression from non-degenerate perturbation theory for the corrections to the first order corrections to the wave functions. And if you recall, or if you just notice in this formula, in the denominator, we have the difference in energies between several states. So if that difference happens to be zero, which would be the case if states N and M here were what we call degenerate, having the same energy, then this expression would have a division by zero and wouldn't give us a proper wave function for the first order correction. So the expression at right in non-degenerate perturbation theory won't work if two or more of the unperturbed states have the same energy, since the denominator then goes to zero. And it turns out that in this case, for those particular states that have that problem, even we can't trust the first order corrections to the energy either. If we can't trust the first order corrections to the wave functions, we can't trust the first order corrections to the energy. So we need to have a different strategy when two or more of the energies of our unperturbed states have the same energy. Okay, so what's happening is the perturbation H prime, which we add to our original Hamiltonian, what we say, it lifts the degeneracy between the unperturbed states. So if we look here, as we have the unperturbed states here, we have two states with the same energy. As we put on the perturbation and the parameter lambda, which controls the strengths of the perturbation, goes up to 1, the states which have the same energy with the perturbation split and don't have the same energy. So conversely, as the expansion parameter lambda is dialed back from 1 to 0, as we go back from having the full perturbation back to the unperturbed Hamiltonian, the exact solutions for the states with the perturbation will limit to some linear combinations of the unperturbed states, which share the same energy E0. It may not be the states that we start with, but it would be some linear combinations of those unperturbed states, which the exact solutions will limit back to as we go back to lambda equals 0. And it turns out that if we can find these linear combinations, we can use them to get the first order energy corrections using this formula here, where instead of the states which we may start with, we use the linear combinations. This formula, which is X'd out here, will actually be valid and give the first order perturbation to the energies. Okay, so let's look at an example. We have a two-dimensional harmonic oscillator. It has a Hamiltonian H0 is p squared over 2m plus 1/2 m omega squared, where m omega squared is basically k, or in fact is exactly k, times x squared plus y squared. So it's in the plane with x squared plus y squared being the distance squared from the origin. So it's a 2D harmonic oscillator. And we put on our perturbation H prime is epsilon. So the strength of the perturbation is controlled by epsilon times m omega squared xy. Okay, so we perturb it a little bit from this original 2D harmonic oscillator. Okay, so the ground state of this would just be taking the ground state of, because this Hamiltonian separates nicely into x and y parts if you try to solve the TISE for it, would just be psi 0 of x times psi 0 of y, where psi 0 of x is the ground state of the 1D harmonic oscillator, and psi 0 of y is the ground state of the 1D harmonic oscillator in the y direction. But there's only one of those states, so we don't get a degeneracy there. So we can apply, for example, for that ground state, we could apply regular non-degenerate perturbation theory with this perturbation to get the shift in energy for the ground state. But the first two excited states of the unperturbed Hamiltonian H0 will have an energy, E0 is the ground state energy of one of the two coordinates x or y, which would be 1/2 h bar omega plus 3/2 h bar omega, or 2 h bar omega. Okay. So the energy of the ground state would be h bar omega. The energy of the two first excited states is 2 h bar omega. Now, why are there two states? Well, we can either pick the not single particle, but the one-dimensional ground state to be paired with the x coordinate, so psi 0 x, and the one-dimensional excited state psi 1 to be paired with the y coordinate. And that one we call psi 0, let's say A. And that written out would be this. It turns out, if you write out the ground state in the first excited state multiplied together. And the second one would be where we take the one-dimensional excited state psi 1 and pair it with the x coordinate, and the one-dimensional ground state and pair it with the y coordinate. And that we get the same wave function, but we get an x here because the first excited state of the one-dimensional has an x out in front here. Okay, so so we have these two first excited states, and they are degenerate because they both have the same energy here. So we need to, if we tried to apply non-degenerate perturbation theory here, we couldn't trust the answers using these states psi A0 and psi B0, or we wouldn't know that we would get the right answers. So in this case, it turns out it's possible to solve for the exact eigenstates of H0 plus H prime. That's possible here. It takes a few lines. You can see the text for the exact solutions with the perturbation present. But we find when the perturbation H prime is dialed back to 0, as we talked about here, the linear combinations from these exact eigenstates which we get, the linear combinations which remain when we dial this perturbation H prime back to 0, which still share the same energy, so that they're still degenerate, but they're the continuation of the exact solutions as we dial that perturbation back to 0, are given it right. So right here, so psi 0 plus and minus, which is 1 over the square root of 2 psi b, either plus or minus psi a. Okay, so we take some linear combination of these two, and the 1 over square root of 2 factor is just to normalize the the resulting wave function so that the the square of its wave function of this wave function integrates to 1. Okay, so for this particular case, we can take the we can actually figure out from solving the problem exactly for the perturbation what states here are the limiting states as we come back to the to be without the perturbation. Okay, in most cases we can't do that, but here for this case, this is a good example to look at because we can check our work on the two methods that are often used to find these linear combinations in the case where the more common case where we can't solve the perturbation exactly. Because after all, that's what perturbation theory is for estimating what the solution is when we can't solve exactly. Okay, so the first method we can use is called diagonalizing the perturbation in the degenerate subspace. Sounds pretty fancy, but in practice, it kind of makes sense. So as we said, usually we can't solve the problem exactly like that, like we just did for the 2D harmonic oscillator with that perturbation. So we want to find the right linear combinations, psi 0, sum alpha times the first state we have, the first degenerate state we have, plus beta times the second degenerate state we have. So to do that, we can expand the our full problem with the perturbation in it. So H is H0 plus H prime in orders of lambda, just as we do in non-degenerate perturbation theory. Okay, and so we go through some expansions and collecting of terms and stuff, and you can see the text for that. And what we find is after we do the expansions and take some inner products with these states psi A0 and psi B0, is we find this kind of matrix equation. But we'll see that it's a matrix equation in a second. That this coefficient alpha that we're looking for, which is the coefficient of the first unperturbed state we have in the desired linear combination, which we're looking for, plus beta, which is the coefficient of the second unperturbed state we have, times times WAB is equal to that alpha times E1, okay? Where E1 is the correction of the first order correction to the energy that we're looking for, okay? So what are these coefficients W? Well, Wij is the matrix element of the perturbation in between the state psi I0 and psi J0. So for example, with I equal A and J equal B, this would be psi A0 H prime psi B0, or WAB. So it's the matrix element of the perturbation in the two unperturbed states we have, psi A0 and psi B0. So this WAA, we would have an integral to do with psi A0, the perturbation H prime psi A0 on the other side. So to get each of these coefficients, WAA, WAB, WBA, WBB, we would have to do 4 integrals to do that, which is doable, but you know, sometimes these integrals are a little bit challenging. So, but it's often doable. Okay, so we have this equation here, and it kind of looks little matrix-like. And in fact, we can write these equations, these two equations, in a matrix form, where we have a, assuming we do these integrals to get the known coefficients, we have a matrix W times a vector alpha beta is equal to the this energy E1, which is the first order correction to the energy, times alpha beta again. Okay, so this is an eigenvalue equation where we have a matrix W times a vector is equal to E1 times the vector back again. And so turns out the eigenvalues E1 of this matrix equation give the first order corrections to the energy, okay, in the degenerate perturbation. And this is called the degenerate subspace because alpha and beta, when we look this psi A0 and psi B0, the different linear combinations of it form a subspace of the full set of wave functions, which are the eigenstates here. So this is the degenerate subspace, is all linear combinations of these two. That's why we're saying we're diagonalizing the perturbation in the degenerate subspace. And the eigenvectors give the coefficients alpha and beta of the right linear combinations of the original states we have, or the unperturbed states, psi A0 and psi B0. Okay. So, so we just have to calculate some matrix elements and do this eigenvalue problem, and we get the two eigenvalues which we get will be the two first order corrections to the energy, and the two relevant linear combinations which have those corrections to them are given by the eigenvectors alpha and beta, the two sets of alpha and beta. Okay, so going back to our example, for the 2D harmonic oscillator, the matrix equation turns out to be, so if you do these integrals using the psi A0 and psi B0, which we looked at before, the combinations of psi 0x, psi 1y, and psi 0y, psi 1x for psi b, and you do all these integrals, you get this matrix here. Epsilon h bar omega over 2 with 0, 1, 1, 0. So this is our matrix W. And it turns out this has eigenvectors 1 over the square root of 2, 1, 1, a normalized eigenvector, 1 over square root of 2, 1, 1, and 1 over the square root of 2 minus 1, 1. Okay, but notice that if we look at what this gives, this is actually the same linear combinations we found previously by solving the problem exactly and extrapolating back to where the perturbation went to 0. Namely, it's psi plus or minus 0 is 1 over the square root of 2 times psi b0. So psi b0, because each of these lower entries in these eigenvectors is 1, and plus or minus psi a0, because the first one is 1 and the second one is minus 1. So when we multiply this, when we express this in the basis of psi a0 and psi b0, we get these two states, psi plus and minus. And that's exactly the same two states that we saw before. Here, again, extrapolating back from the exact solutions, we got these same two states. So that checks out in this case, which is good. The eigenvalues, which are associated with these two eigenvectors, give the first order corrections to the energy, which are E1 equal plus or minus epsilon h bar omega over 2. So the upper state, psi 0 plus, with the plus sign here, has an energy, a higher energy than, so the first order correction is positive, and the psi b0 minus psi a0 has a negative first order correction. So the two states split with the perturbation. One state, one linear combination, the one with the plus going up in energy, the other linear combination going down in energy. Okay. So that's method one, is finding this matrix W from the states that the unperturbed states that we have, doing an eigenvalue problem, taking the eigenvectors to get the linear combinations we want, and then the eigenvalues are our corrections to the energies. The other method, which can save us from doing some integrals, and because those integrals sometimes to get that matrix W, are doable in general, but are lengthy. So it turns out if we can find a third operator, A, that commutes with our unperturbed Hamiltonian and our perturbation, we can kind of take a shortcut to get these states, these desired linear combination states. So there's a really nice theorem which says that if A is an operator which commutes with both H0 and H prime, then psi A0 and psi B0 are eigenfunctions of A with distinct eigenvalues mu and nu, and these two states are eigenfunctions of A as well as being eigenfunctions of H0 and H prime, with distinct eigenvalues mu and nu, then if they have those distinct eigenvalues, then psi A0 and psi B0 are in fact the desired states, the desired linear combinations. And we can use that psi A0 and psi B0 in non-degenerate perturbation theory. So the basic non-degenerate perturbation theory formula that we just take the matrix element of psi A0 or of H prime in psi A0 to get one correction, and the matrix element of psi B0 to get the second correction for those two states. So, okay, so what kind of operator would this operator A be? Well, it's usually what we call a symmetry operator. It's not like momentum or energy or something like that. It has to do with some symmetry of the coordinates. Exchanging coordinates or rotating the system in some way. That's what we mean by a symmetry. So as an example, for the 2D harmonic oscillator, which we looked at before, this was the unperturbed Hamiltonian here, and this was the perturbation. An operator D, which exchanges X and Y, it turns out commutes with both H0 and H prime. And we can see that because if we look at H0 and H prime, if we just switch X and Y here, remember D exchanges X and Y, we get the same thing back again. Okay, so this is commutes with D because D doesn't change H0. And similarly, the perturbation, if we exchange X and Y, it doesn't change H prime. So the operator D commutes with both H0 and H prime. So we're looking for states psi AB and psi B0. Well, we're looking for two states which are eigenstates of D, or eigenfunctions of D with distinct eigenvalues. So we can start by looking at the two states which we had before, which were psi A0 is psi 0x psi 1y, and psi B0 is psi 1x psi 0y. Okay. So what do we get when we operate with D on those states? Well, let's see. D on psi A0, x and y. Remember, D exchanges x and y. So it's going to give psi A0 of y and x. But if we switch y and x, if we look at that, that would be we get psi 0y, psi 1x. But that's exactly what we have over here for psi b, is psi 0y, psi 1x. So that's actually psi b0 xy. And similarly, if we operate with D on psi B0, X and Y, we get psi B0, Y and X, which is going to be switching X and Y here would be psi 1 of Y, psi 0 of X, which is exactly what we have for psi A0. So when we operate with on these two states which we started with, we don't get a number times psi A0 back again. We switch the states. So these two states are not eigenstates of the operator D. However, it turns out that the states which we looked at before, which is probably not surprising because we're working with the same system, but if we combine the states in linear combinations, so psi plus or minus is plus or minus psi A plus psi B, those are eigenstates of D with distinct eigenvalues plus or minus 1. So to see that, we can operate with D on this state plus, or these two states plus or minus psi A plus psi B. So when we operate with D, D distributes in, so we get plus or minus D psi A0 plus D psi B0. We already showed that D on psi A is psi B, so this would become plus or minus psi B0. And this would become just psi A0. But this can be written as plus or minus the plus or minus psi A0 plus psi B. Okay, because if we take the upper signs, we get psi A0 plus psi B, which is what the top state here. If we take the minus the lower signs, we get psi A0 positive minus psi B0. Okay, so so these are the eigenstates of D with distinct eigenvalues plus or minus 1. So when we normalize these states, these two states, these are again the two states we found before. The normalization factor is 1 over square root of 2, it turns out. And we just kind of write it as we've found them before, with psi B0 to the left and plus or minus psi A0 to the right. So those are the same states as we found previously. And with those states, notice we haven't had to do any integrals here. We just had to find eigenstates of a symmetry operator. So if we're able to do that, we can use these states once we know that we have those two states of the symmetry operator with eigenvalues, distinct eigenvalues plus or minus 1. Those must be the states we need to use to find the first order corrections to the energy. So we could use those in non-degenerate perturbation theory. Take the expectation value of psi plus with the perturbation h prime. We would get plus epsilon h bar omega over 2. Take the expectation value of psi minus, and we get with the perturbation h prime, we get minus epsilon h bar omega over 2. Okay. Okay, great. So that's in a nutshell degenerate perturbation theory. Again, it comes about when we're trying to when we're trying to deal with a problem where we have two or more energy states with the same energy. And we can find an exact solution sometimes. In this case, with the harmonic oscillator, we were able to find an exact solution, which we used to check our two methods, which were first diagonalizing the perturbation in the degenerate subspace. So we find these matrix elements of the perturbation in the states we have, and the eigenvectors and eigenvalues give us our proper states, which we need, and the corrections to the energy. And then the shortcut method, which we can sometimes use to avoid doing those integrals, is to find a symmetry operator which commutes with both our original Hamiltonian and um, our perturbation H prime. And if we can find eigenstates of the symmetry operator with distinct eigenvalues, we automatically have the states we need, and we can use non-degenerate perturbation theory to find the corrections to the eigenstates, the first order corrections to the energies. Okay, so that's an overview of non-degenerate perturbation theory. Thanks for your attention to this, and I hope it's been helpful. And I will see you in class.